Hello everyone, my name is Lee from KAIST, South Korea. From now, I'm going to present our Beyond Communication, On-Modem DNN Inference and Training for Home Appliances. Let me start with background and motivation of our work. Recently, many smart home appliances are increasingly integrating AI technologies to deliver intelligent services. Instead of simply performing fixed functions, modern appliances can now perceive their environment, learn user preferences, and make autonomous decisions. By leveraging AI techniques such as computer vision and speech recognition and machine learning, these applications can adapt to users' daily routines and provide more personalized experiences. One way of realizing the smart home appliances is to utilize cloud-based AI. Currently, many commercial home appliances collect user data at home and send them to the server where the data is learned by DNNs, deep neural networks, to provide intelligent services. The results learned on the server are then sent back to each user at home, sometimes via user devices such as smartphones. So by delegating arduous learning tasks to the resourceful server, home appliances can learn usage patterns of customers and offer data-driven intelligent services over the network. In order to connect with cloud servers for AI processing, smart home appliances typically use some communication modem modules, such as Wi-Fi. These modem modules act as gateways that transmit user data from the appliances to the cloud and receive the processor result in return. Through this communication, appliances can provide intelligent services without requiring powerful AI computation directly on the device. However, according to the consumer electronics manufacturers such as LG, Samsung, Whirlpool, from 80 to the 90% of the smart home appliances are never connected to the network, meaning that AI-based intelligence services are not offered to most customers. Another important implication of this phenomenon is that the modem hardware, for example, Wi-Fi module built in home appliances is never used at all. So in this work, we propose on-modem learning, which is a framework that enables DNA inference in training directly on commodity modem modules. For example, Wi-Fi modules in home appliances. Instead of using the modem solely for communication, we repurpose it as a self-learning module capable of performing AI tasks locally. By leveraging idle computing resources on the modem, and now appliances can run small DNN models, deep neural network models, and learn from user data without fully relying on the cloud. To the best of our knowledge, the proposed on-modem learning is the first standalone approach, enabling AI learning directly on commodity modem modules in home appliances. However, in order to realize on-modem learning, we need to overcome several challenges. The first challenge is the data oblivious modems. Basically, modems are originally designed for data packet transmission without understanding payload semantics. And manufacturers deploy the identical firmware to the identical firmware across diverse appliance models that generate heterogeneous data types. So here, the key challenge is that how to enable unified semantic parsing of data by using only a single format. The next challenge is about efficient on-modem DNN training and inference. So because modem modules usually do not have sufficient computing power or memory and other resources to perform DNN training inference. So here, key question is that how can DNN training or inference be performed efficiently on these constrained home appliances? In this work, we tackle these two challenges. The first challenge is the data oblivious modems. Modem modules are, again, originally designed only to transmit data without understanding of the semantics of the payload data. In other words, the modem do not care about the meaning of each byte it carries. Furthermore, in practice, manufacturers also only deploy identical modem hardware and firmware across many different types of appliances models, even though each appliance produces different data formats. So because of this, embedding product-specific translation tables into a single modem firmware becomes impractical. As a result, data translation is typically performed in the cloud, which limits the ability to feed the correct data directly into the on-modem learning process. In order to address this problem, we propose LSTM-based data payload parser that sequentially analyzes raw data bytes and classifies them into semantic data fields, such as temperature, status, or the course number of the washing machine. So this eliminates the need for translation table and enables semantic data understanding and interpretation for all modern DNA inference and training across diverse appliances. Now, data is ready. So now the model can understand the meaning of data. And then the next challenge is to perform resource-intensive DNN training as well as inference on resource-constrained modems. In order to enable on-modem DNN training, especially in a resource-efficient way, and DNN model adaptation toward user data of each home appliances, we propose three on-modem training methods. The first one is the grid and diverse gradient accumulation, GDGA in short. And second is the dynamic programming-based backpropagation, DPBP in short. And the last one is the on-modem reinforcement learning, OMRL in short. So they collectively allow memory and compute efficient on-modem training of DNN. The first method is greedy and diverse gradient accumulation, GDGA. Basically, training a neural network with backpropagation requires a large amount of memory, which far exceeds the capacity of many commodity modem modules. They typically have only kilobyte to the megabyte of memory. Actually, a major bottleneck comes from the mini-batch gradient accumulation, where gradients from multiple samples must be stored in memory before updating the model weights. In order to address this issue, we propose GDGA. The key idea is simple. So instead of storing the gradient for the all weights, GDGA selects a small number of the important weights, actually n number of weights, those with the largest absolute values, and accumulates gradients only for them. The remaining weights are updated immediately using the gradient from a single sample without gradient accumulation. So by restricting the number of accumulated gradients to a very small subset, and here GDGA significantly reduces memory usage during training. For example, in a 5-layer network with 256 neurons per layer, so actually GDGA can reduce the memory requirement up to 300 times. So this level of memory reduction is difficult to achieve with conventional compression techniques such as quantization or pruning. The next is the dynamic programming-based backpropagation, DPBP. Many commodity modems do not have enough computational capability to efficiently perform compute-intensive backpropagation during DNA engineering. To address this, we propose DPBP. Uh, here the key idea is to reuse intermediate gradient computation, which is colored as gray, during backpropagation. Since many ways to share common components in their gradient calculations in gradient chain, repeatedly computing them leads to unnecessary overhead. Specifically, DPBP applies dynamic programming to store and reuse these intermediate results, so it can avoid redundant calculations. So as a result, the gradient update process becomes significantly more efficient, allowing DNNs to be trained much faster, even on resource-constrained modem hardware. For example, more than 1,000 times. The last one is the On-Modem Reinforcement Learning, OMRL, which is conducted for the personalization of the DNA. Actually, a standardized DNA pre-trained by the manufacturer often cannot provide personalized services because users have different usage patterns and appliances dynamics may change over time. To address this, we propose on-model reinforcement learning or OMRL. Actually, the OMRL allows the modem to continuously fine-tune or pre-train the DNA using online user data. It leverages reinforcement learning, especially temporal difference, to adapt the model to individual users and changing appliance conditions. So from the user's perspective, OMRL process is fully automatic and transparent since it does not require manual data labeling or human supervision. As a result, appliances can continuously learn and improve their services directly on the model. We implement on-model learning on the real-world home appliances, that is, LG washing machine. We implement two real applications of on-model learning onto the washing machine. The first one is the remaining watch time prediction, and then the second one is the unbalanced error UE focus, which are executed with two small size DNNs on the modem. The fourth application is the on-modem learning is the remaining watch time prediction. Actually, providing an accurate estimate of the remaining watch time is important. However, predicting the remaining watch time is not straightforward. The total washing time depends on many factors, such as the type and amount of laundry, wash conditions, water level, and selected washing options. Actually, these factors vary across users and washing machines, and they also change over time. As a result, the traditional prediction algorithms used in commercial washing machine often fail to capture individual usage patterns and evolving appliance conditions. To address this problem, we implement an on-modem DNA application that estimates the remaining wash time. So here, our model is continuously adapted at runtime during in-situ data generated during the washing process. Using OMRL, the system adapts to each user and washing machine during the washing operation, enabling personalized and continuously improved predictions. The second application of on-model learning is the unlabeled error UE focused. During a washing cycle, the drum of the washing machine rotates at high speed. So to ensure safe operation, the balance of the washer and laundry load must be maintained. To prevent this, the modern washing machines include a mechanism that detects unbalanced condition, UE. So when this occurs, the machine generates UE or unbalanced error, and immediately stop the washing operation. However, the limitation of the existing system is that the UE warning is triggered only after the washer has already become unbalanced. So we implement on-modem learning application that can forecast the UE before the washer actually becomes unbalanced. So this proactive prediction helps prevent unexpected interruptions of the washing process and potential damage to the appliances, providing a capability that is not available in current commercial washing machines. So with this early warning, users can take preventive actions such as redistributing the laundry or adjusting the washer before problem occurs. In order to implement on-modem learning, we collected about 6 million user data samples from real customers of LG Electronics as shown here. Now let me discuss about the evaluation result of the two applications. So here this table shows compares the prediction accuracy of our method with the existing commercial algorithm function using MAE and then the absolute errors. The results show improved accuracy. The commercial algorithm achieves 4.428 MAE, and while the our method applying the OMRL achieves 3.346 by adapting to the runtime user and washer data. So this bottom figure shows the runtime adaptation of the on-modem DNN over 6 washing operations. The model is continuously updated using the runtime data through temporal difference learning. As the washing progresses, the prediction becomes closer to the grounded truth remaining time, which outperforms the existing algorithm. For example, when actual the remaining time is the 64.9 minutes, the the predictions made by our method is the 64.1 minutes, while the existing method estimated as the 56 minutes. So this shows that the adaptive or modern DNN can learn user patterns and washing conditions to provide more accurate predictions of data over time. So here, the left table shows the classification accuracy of the UE forecasting application using different input sequences. Overall, the model achieves very high accuracy around 0.99 average. So here, right figure shows the confusion matrix, which categorize the prediction into 4 classes, which also shows the good performance. So let me conclude this presentation with discussion and limitations. The first, the proposed on-model learning can be also applied to connected home appliances. And also, another important aspect is the scheduling with communication tasks. So as future work, the more advanced scheduling mechanisms should be developed to enable seamless integration between on-model learning and communication tasks. And finally, there are some opportunities for other applications under resource constraint. Thank you so much. If you have any question, please let me know. Thank you.